welcome everyone to the latest webinar from the DRIIMB Consortium. So just a reminder for those that are maybe not so familiar, DRIIMB is a consortium funded by the UKRI digital research infrastructure, looking at building data and software bridges between structural biology techniques, in particular looking at crystallography, cryo-EM, NMR, and biomolecular simulation. And these are represented by their respective CCPs, which are collaborative computational projects. But one of the things that DRIIMB is very interested in is building bridges outwards to related communities, both in biology and in technologies. So in that spirit, I'm delighted to welcome Andrew French to talk to us today, and he fulfills both of those criteria, having his own interesting biological research, and also being director of AIBIO-UK, so looking to promote AI technologies within the biosciences. He's a computer scientist by training and is leading the computer vision laboratory at the University of Nottingham. So I believe he's going to talk to us both about the activities in the computer vision laboratory and a background to AIBIO-UK. So with that, can I hand over to you, Andrew? And
yeah, thank you very much for the introduction, Martin. And thanks everyone for joining. I hope I've got a couple of interesting talks for you. As Martin suggested, I think it's probably a bit outside your normal field, certainly normal scale of looking at data, but hopefully there'll be some things of interest, and you never know what's going to cross over to another discipline. So what I thought I would do is I would first of all give you a talk about what we're doing within the computer vision lab in Nottingham. So I've just got a few projects to talk about. My background is in computer vision, image analysis. That's my research work, if you like, and what I teach. So how to get information out of images in different ways. And we work with loads of different kinds of images in CVL. And so I just wanted to produce present a kind of varied set of examples of how we're working with some bioscience data at the moment. In the second half of the talk, I'll talk to you about AIBIO, so the AI in Biosciences BBSRC network, which has been running 2.5 years now, thereabouts. It's coming up to about halfway through. So I'll tell you a bit about who we are, what's coming up, and how you might want to get involved in that. So first of all, about the computer vision lab. So yes, we're based in Nottingham at Jubilee campus. For once, the weather on the photo is actually matching the weather outside my window, which is a pleasant change from all the rain. So we are based in computer science at Nottingham. We are developing these days a lot of core AI approaches, machine learning approaches to computer vision, right? So we've obviously I've been doing this for quite a few years now, and we've started off with very classical programming of sort of stepwise solving of image processing and computer vision tasks, through to more machine learning, feature engineering type approaches. And nowadays, I think probably 90% of what we do is core modern AI, so deep learning and transformers and things like that. But as you'll see, there is some classical computer vision in there as well. We've got, I think, just upwards of about 20 group members at the moment, PhD students, academics, researchers. About half of us are working in specifically plant-related data. So we do a lot of what's called plant phenotyping work, measuring as much as we can about different kinds of data to do with plants. Everything from subcellular stuff right up to what's happening out in the field. So the real kind of range across scales there. So I've picked a couple of different projects to talk about, one at the cell scale and one at the plants scale to talk about. We've got our own computational resource, so we've got our own GPU computer at Nottingham, which is very much an in-house compute system, shall I say, that we've kind of grown up over the years, keep adding to it, and it's kind of become a challenge in itself, keeping it going, but it's also core to what we do and the deep learning that we develop. So that's us. The rest of the group are looking at a variety of different data, everything from medical image analysis to human-facing stuff and self-driving cars and things like that. So biosciences, plant biology, probably about half of the group. So the three projects I was going to briefly show you today. So one is cell scale work. So taking images like this of plant cells, and I'll show you how we capture those in a minute. And then obviously the challenge being, once you've got the image, how on earth do you measure, count, somehow label all the different cell types that you've got in that kind of image. The second one's more about kind of organism scale work. So looking at actual plants in pots in this case, and how do we do 3D reconstruction of those plants? So how do we turn 2D images into a 3D model? But also thinking about synthetic data, which is something that might cross over into your world a bit more. Training AI models is hard, needs a lot of data. And so one thing that we're doing in CVL is coming up with ways to help train AI algorithms by using fake synthetic data that helps the model get to where it needs to be. Lastly, I'm going to show you who owns this foot, and I'll just kind of tantalize you with that for now. Right, so first project then. So this is project work that's been done by a few of our postdocs, Yafei and Janet, developing computer vision approaches to analyze images that look like this. So these are laser ablation tomography images of plants. So zooming in, you can see it's a little bit blurry, and you'll kind of see why in a minute when I show you how they're captured. But basically, we're looking at autofluorescence of plant cell walls as a laser is cutting into the plant. So we end up with a sort of a 3D stack, if you like, as the plant is being literally, I guess, burnt away by the laser. And the laser's also making the cell wall of the plant fluoresce, which is why we're capturing this blue color here. So what we're looking at is basically, if you imagine kind of looking down a stem, and then the laser's hitting the end of the stem, and so we're getting essentially a series of cross sections through the stem of the plant. And you can image all kinds of different plants like this, and not just plants, other structures as well. And it's quite a unique kind of imaging setup. The system itself looks like this. So it's all housed in this device here. I think I'm right in saying Nottingham was the first place to gain one of these laser ablation devices outside of the US. So it's been it's a commercial system, but it's also been a bit of development work, I think, getting it going over the years. And that's based in what we call the Hounsfield facility, which is nominally a kind of micro CT imaging facility at Nottingham, normally used to look at micro CT images of plants in soil. So taking X-rays, 3D X-rays of plants growing in soil. Why would you want to do that when you can see the root system without disturbing the root system? So you can see how it's growing around rocks and through air gaps, and how it responds to different moisture levels and things like that. So this is housed in that facility, but a very, very different kind of imaging process. So you can see the plant kind of restrained here. This is very much in the kind of James Bond Goldfinger position. So we've got the laser here, and then we've got a microscope objective here, and you can see it's literally burning its way down, if you like, the stem of the plant and capturing those images as it goes. So the laser's both destructively working through the sample, but as an artifact of the laser, it's making the plant fluoresce, and then that's captured via this microscope image. So a bit more about the system and what it comprises. So it's using a UV laser to do this. There's obviously a lot of robotic stage work to move the plant into the right position and keep the lens, microscope objective lens lined up and things like that. What's being captured, so the light from the laser is going through one of a number of different lenses. I'll show you some images of different zoom levels in a minute so you can see what they look like. But it ends up in one of these machine vision cameras, and then we store, essentially it's a set of frames that you can either view as a video or you can kind of think of it as a sort of 3D structure. And yeah, this was funded through BBSRC Alert and has got various kind of custom LabVIEW interfaces to help with data capture. Darren, who built the majority of the system, would tell you there's quite a complicated kind of sample preparation procedure to get things onto this. But I don't know a lot about it other than there's a lot of kind of pre-work in getting samples to the state where you can actually do this and get a nice image out of it. So I mentioned it has different microscope objectives that it's using. So different zoom levels give us different levels of detail. So here you can see the sort of full outside of the stem. And then as we work up to really high detailed structures, you can see a lot of cellular cell wall detail and things like that in the highest zoom level. You'll notice that there's quite a lot of variety in the brightness as we look through the images. So I guess that's an artifact of how well the different structures are fluorescing, but it's also a bit of an artifact of the capture process because it's essentially being captured as a video rather than a set of discrete images. You do tend to end up with bright bits in the image and darker bits in the image. So you can see here, this bit's quite a lot brighter than the left-hand side here. So we come back to that when we talk about how we process the images in a minute. But that's essentially what we're working with here. So although they're color, really you can think of them as a grayscale image because it's all essentially the same blue hue that we're getting fluorescing back, certainly with the plants that we're working with. So yeah, the challenge is how do you go from these wonderful looking images into actually numerical data that we can work with? There's a lot of cells here to count or annotate by hand, so we want to try and automate that process as much as we can. So the process is basically done in 2 steps. So Yifei, who developed the approach along with Janet, they kind of worked out that these images are, first of all, they're really quite big images. And so there's a challenge, if you're building an AI system, there's a challenge in getting ground truth data, because to train some kind of segmentation labeling model to get an output that we want, which is like, looks like this, where we've got different types of cells marked in different colors. It's very challenging to get ground truth data for that because the traditional way of doing it is the poor biologist marking around every single cell by hand in order to get the different labels out accurately. So that's one reason why there's a 2-step process. And the other reason is the importance of the structural information in the image. So what we want to do is we want to turn these lat images into something that's much more just structurally a kind of binary black and white image. So we're throwing away all the variation in the brightness. As I said, the image capture gives you that kind of natural variation in brightness across the image. We want to throw that away and we just want the structural information. So we just want kind of where are the cells? That's the important thing, not how bright they are or fine texture detail. And we found working with the plant scientists that there's plenty enough information in these sort of intermediary images to be able to identify different cell types. So it's a 2-step process. First of all, we get a binary image out to simplify the problem. So that's done using something called adaptive thresholding. So I mentioned those kind of classical computer vision approaches. This is one of those. Anyone who's done any work with image analysis at all, probably the very first thing you learn to do is thresholding. Really simple. If something's above some kind of brightness level, you mark it as foreground versus background. And you can do that across the whole image with one set threshold value. And if it's above that, it will mark it as cell wall in this case. Now that's a problem where you've got illumination variation across an image because that threshold value will change across the image. And that's where adaptive thresholding comes in. So you can use adaptive thresholding techniques to look at a little window on an image and say, well, what's the best threshold value sort of over here in a darker bit versus over here in a brighter bit. So there's some classical pre-processing done on adaptive thresholding to get this intermediate image out. And you can see that it's also producing a lot of noise in the background. That's what adaptive thresholding does. That doesn't matter. The next stage, the AI bit will fix that for us, thankfully. So here we're focusing on tissue boundaries and structure rather than anything else. That's stage one, okay? So we take our original image and we produce this binary image here. We get there via doing adaptive thresholding and use a UNet to produce a binary output here. What we want to get is this multicolor map down the bottom here. So the second stage of the pipeline takes as input this nice black and white map, along with some other kind of pre-processing channels, if you like. Some adaptive thresholding or gradient information can be fed into there, again, to get the structure out. And then this second process kind of works in a similar way, but it's got this extra refined input that goes into it and then produces the multi-labels coming out. But what's nice is because we have this intermediate stage that doesn't require any supervision or pre-labeling, we can then get our friendly plant scientists to much more easily produce some colored ground truth for us. So rather than having to draw around each cell, what they can do is they can kind of paint in by using kind of broad sweeps of a paintbrush, if you like, the different colors without having to supply the structural information. So they can just say, yeah, this region here, this is one particular cell type, that's another cell type. So they can use brush tools in a tool that Janet and Yafei have built to quickly color in this black and white image. So they're not having to be too concerned about where fine boundaries are around cells, rather they're using the semantic information. What cluster of cells does this represent? So that massively speeds up their ground truthing of annotation of data. And what we can do with that then is feed that back into the full system to train our multi-class output. And that works really well. So that two-stage output works really rather nicely. So as some examples, we've got a few different plants. You can see the original lat image here. Here's the ground truth. And then here are the predictions that are being made by the model. And it's actually a really hard problem, this. There's a lot of subtleties to do with this distinction around sort of these three layers here, for example, that's quite hard to pick out if you're not a plant scientist, which I'm not. You can see that the AI does a pretty good job of localizing those regions pretty well, even in, quite, if you like, distorted samples like this. This is not a nice, neat, clean, circular sample, and it's still managing to label it pretty well. A nice side effect of this is because we're pre-processing the image to get the structural information out, the cell centers and the cell boundaries, we can actually get it working on other image types. So as well as laser ablation tomography, this is a CT image. So this one's X-ray derived rather than using the laser. Very different looking raw image if you can compare them. But actually, because we're going through that pre-stage where we're getting the structural information out, actually we can get it working really nicely on those as well. So the model generalizes surprisingly well, which is always a nice side effect. I mentioned a tool. We've written quite a few software tools in the computer vision lab. And again, this one allows the biologists to both annotate the data and also run the tool on new images. We've tried it on a number of different plants, quite different looking, as you can see. And again, in this case, comparing the binary images coming out, comparing a kind of naive baseline model versus our approach. Hopefully you can see that ours are quite a lot sort of neater, better refined boundaries, and it's better segmenting the cells, especially in the darker regions, which, depending on the system you've got, are the bits that it's going to struggle with. And here's some colored multi-class results of the similar kind of thing. Even this one here, which is really really quite kind of messed up as the sample, it still does a pretty good job with that. And you see that more naive approaches tend to bleed out the different categories. They're not as sure at where the different cell types should be, but your phase approach is much better at doing that. Okay, so that was one example of a cell scale project with some pretty challenging data, that, you know, a pretty unique image capture system that we've got at Nottingham. What I'm going to come on to now is something completely different. So different scale, different use case. It's still plants. And what we want to do here, it's kind of a mix of plant phenotyping, measuring what we can about growing plants. It's a bit about 3D reconstruction. So how do we take a complicated 3D object in the real world and build a model out of it that we can then use in a pipeline of analysis? But there's a little bit of computer graphics and data representation here as well. So this approach that Lewis and Zane have developed is using something called Gaussian splatting, which probably haven't come across in your world very much. But it's a very big thing at the moment in sort of the movie industry, capturing 3D models of things quickly. If you know anything about capturing 3D models from images, so photogrammetry, stuff like you can do with smartphones quite easily nowadays, this is kind of a bit of an extension of that. So this is a way of getting really nice 3D models out of a set of images. One of the challenges we're looking at here is being able to produce synthetic data. So I mentioned that one thing that we want to do when we're training AI algorithms is to have a large data set of data to train them with. And that's challenging with 2D data, but it's even more challenging with 3D data because it's that much harder to collect image data sets. So one thing that we want to do here is, as well as being able to refine and get a very nice 3D reconstruction of a real plant, we want to be able to say, well, can we also produce similar data from an artificial model of a plant as well, so that we could use that further down the pipeline to train some sort of 3D algorithm that maybe is segmenting the leaves or the stems or something like that. So capturing real 3D data is very challenging and expensive. You need lots of plants, you need complicated imaging setups. So to do this, Lewis has got a 6 degree of freedom robot arm that will go around a plant capturing loads of images of it. You could do it manually, but it means taking a lot of images all in one go, and it's not very precise to recreate that image capture pattern, if you like, on the next plant. So we've got a robot set up to do that in CVL. And it's just quite difficult to get plants that are behaving, so ones that aren't damaged, or in this case, I think the plant has moved a little bit. So you can see this kind of ghosting effect on the reconstruction. Plants are a nightmare to work with. They're always blowing around. If you're talking about going outside, you've got complicated weather effects, different kinds of lighting, rain, you know, diseases, pests, and all that kind of stuff. Just makes plants, it turns out, quite hard, quite a challenging imaging problem to work on. So what Lewis and Zane have done is they built this framework called Plant Dreamer. So it dreams up plant models. It can generate these 3D Gaussian splats. I'll come on to what those are in a minute, of a wide range of really quite complicated geometry. These can be 3D models that are completely synthetic or based on something called an L system, which is a mathematical way of describing a biological structure like a plant. So we can build it from real world captured point clouds, e.g. from a LiDAR system or from a load of images taken around a plant using photogrammetry, or we can just think the whole thing up, dream it up, hence the name. So the two technologies this is built on are something called an L system. An L system is a mathematical model to describe branching structures. So you can apply it in all different kinds of worlds in biology. We're using it for plants. It makes a lot of sense because plants do a lot of branching. That's literally what they do. So you have this grammar that describes how the plants branch, what the kind of leaves of the plants look like, and various parameters about stem length and branching angle and things like that. And that will allow you to recreate all kinds of different plant architectures. So we can use that to imagine our 3D artificial plant to start with, if we're not capturing our own point cloud. And the second thing that we're building this approach on is this idea of Gaussian splatting. So Gaussian splatting, very simply, it's a volume rendering technique, but it doesn't have surfaces around things. It doesn't have a mesh around the objects. Instead, what it does is it takes something like a point cloud model, which literally just has points in 3D space. So there's no volumetric data, there's no surfaces around the object. What it does instead is it renders these points as a set of Gaussian blobs. Think of them as ellipses, okay? A kind of stretched out circle that has a color and a certain degree of transparency. And it turns out this is a nice way of doing things because you can represent a structure with less points than you need from like a full point cloud, but you can build a lot more information in them as well. So depending on the size and the color and the transparency of the blobs, you can render really nice 3D models really efficiently as well. So it's like a halfway house between just the dots of a point cloud and the full mesh structure or the volume of a full 3D representation. So how on earth does it work? So we start off by identifying a type of plant. So as I mentioned, the L system models, branching models, can be optimized to generate different kinds of architectures. So first of all, we need to know what kind of plant it is we're generating so we can make an artificial model that looks a bit like that. That will describe the branching and what the leaves look like and where to put them and things like that. Or we can capture a 3D reconstruction. So we can get a fairly crude point cloud of a plant and use that as a starting point. Whichever way we do that, we then initialize our Gaussian splats on that data, be it the artificial one or the real one. And there are various algorithms to do that. And one contribution of Plant Dreamer is it's got this extra criteria built into the pipeline, which is using a depth map. So depth map is simply the distance from the camera to different bits of the plant. So you can see that this leaf is much closer because it's red. And as you go further away, things become kind of bluer in color. What that depth map does is we can use it via a device called a control net to help control an AI when it's synthesizing new views of this mesh. Okay, so rather than just using the kind of color render, having this auxiliary information, how far away are certain leaves or bits of the stem, allows us to refine our new kind of generative AI viewpoint or mesh that we've produced from this system. So starting from this initial mesh, this initial viewpoint, we can generate new ones from that, is the core idea. And this thing called a LoRa or low rank adaptation is a way of, it's a kind of a training trick where you're able to train an existing very complicated high parameter model with just a few examples. So producing images like this is very complicated and you need a powerful model to do it. But by using a LoRa with a few examples of the plants here, we can get it to produce some data without having to build an absolutely enormous model from scratch. So it's a retraining technique. And that's, again, quite commonly used in generative AI. And the plants that come out, the synthetic plants that come out are quite nice looking. There's also some nerve-based approaches. So it's been a fast-moving few years in 3D reconstruction. So nerves or neural radiance fields slightly predated Gaussian splats. And they were another way of representing 3D models in a very efficient way. But we're using Gaussians here. And the outcomes, the synthetic data that's produced are some really nice looking 3D plant meshes, which we can then use, and we're just doing some work at the moment to then use these to train downstream segmentation tasks. If you want to know more about Gaussian splatting, Lewis has done a computer file video about it on YouTube. So Computer File is, if you've not come across it before, it's quite a good YouTube channel with little 10-minute videos about some quite in-depth technical topics in computer science explained fairly simply. We've recorded quite a few of them at Nottingham. And because it was Christmas, Lewis did one on reconstructing the Christmas tree in our foyer. So you can find out more by going there. I just thought I'd throw this slide in at the last minute because I realize some of what you're doing is looking at maybe a very different scale and different kinds of imaging. So I just thought I'd throw in this different micro CT kind of image, which is, again, it's synthetic data. And what Vicky's doing here is making a pipeline to generate synthetic images, not of 3D plant meshes this time, but of micro CT images. So if you imagine you've got a micro CT volume, as I mentioned earlier, perhaps captured of a plant growing in the soil, and you want to segment where the root is in that soil, it's really, really hard. The rooty bits look like this slightly lighter gray in a background of noise. So again, can we use synthetic data to produce more artificial micro CT volumes that we can train a segmentation algorithm with? Vicky, in her PhD, has been working on using a combination of L systems turned upside down. So we're generating a branching structure for roots rather than leaves this time. And using that inside Blender, which is a 3D modeling environment, to generate artificial micro CT sets volumes, which we can then divide into slices and then train AIs with to do segmentation. So just a very quick kind of shout out to Vicky's work, who's also been doing generative AI, but in micro CT volumes. And we've just had a paper published if you want to know more. And very finally from CVL, the owner of that leg in the third image was this guy. This is inside the Hounsville facility that I mentioned. They've also got their own growth facilities for growing plants. And what we're doing is we're exploring ways of using mobile robotics like this to take that 3D reconstruction approach, for example, into a glasshouse or into a field to start to build 3D models using devices like this. So still early days, but working on building camera capture and data analysis techniques for plant phenotyping using robotics. Okay, swapping hats. So in my other role outside of computer vision research, I'm leading the AI in Biosciences network. So I'm just going to spend 10 minutes telling you about what this network is and how you might be interested in becoming involved in it. So AIBIO has been going for 2.5, 3 years, so about halfway through. We're BBSRC funded. The aim of the project is to bring together AI and bioscience researchers in the broadest sense. So basically anything within BBSRC remit, including things like imaging, absolutely within our remit. And there was a feeling, certainly 3 years ago, that a lot of AI sat outside of this community. And although there were some collaborations happening, it was very piecemeal and there wasn't much kind of information shared across the broad themes of BBSRC. So our aim really was, think of it as a community building project. It's like a networking project, bringing people together, but we've also got some of our own budget for training and pilot projects and things like that. So yeah, we're just trying to bring together AI and bioscience researchers in a whole different range of themes. This is our team. I put the team up because you might know some people that are on it. This is our management team. Although I lead it, we're definitely a community-based project. Okay, all the co-Is are absolutely critical to how it works. And as you can see, we're based all around the UK. We've also got our own research software engineer, Charlie. And I'll come back to that at the end. I'm very keen to explore any potential projects that Charlie might be able to work on as kind of one way of maybe collaborating with AIBIO. We've also got various community working groups that are up and running at the moment, but we sometimes have a refresh of membership. So if you were particularly interested in an aspect of the project, then we welcome you to express your interest, just drop us an email, and next time we refresh one of the groups, we can reach out. So what do? We link with a lot of existing groups and networks. So we'd be very keen to explore any links with some of the groups that Martin mentioned at the beginning in the introduction. We found that a really great way of reaching kind of large numbers of researchers at once is by using existing community groups and holding joint events. So that's maybe one opportunity. We do have a simple sign up form on the website. If you sign up, you'll get an email about once a month summarizing what we've been doing and what's coming up that you may be interested in. Or you can follow us on things like LinkedIn. We've got a few funding opportunities, which I've got a few slides on in a bit as well. We have an annual meeting every year. When we had our last one in May last year, we did a bit of a survey for who came and trying to get an idea of sort of who's kind of actively in the project at the moment. We have quite a good representation from Biosciences, but always keen to welcome more people in, of course. But slightly lacking maybe on the computational side, which could be of interest if you're a computational imaging person. Then definitely your expertise could be very valuable to AIBIO. We're mainly a group of academics, but we do work with industry and UKRI, BBSRC, PSRC, and have links to MRC and things like that as well. And importantly, as I keep saying, we want to represent a complete full gamut of BBSRC research, right? That's our strength. Inside all the individual communities, there's AI expertise. We're trying to provide that kind of umbrella coverage across everything. I mentioned funding opportunities. So we have some pilot funds that have been awarded last year now. So some of these are coming to an end at the moment. Some of these you might recognize. And we've just about finished our second round, but hopefully in about a year's time, we'll be doing our third and final pilot funding round as well. So again, sign up to the newsletter if you want to know when that comes out. But the idea is smallish pots of money that are there to pump prime bigger grants. The core thing that we want is new ideas in the AI bioscience space, ideally with new teams of people putting them together. Something that we've done in the last 6 months as well is some training scholarships in AI and data science. And we've worked with a company called Scriptic to help deliver that. They used to be Learn to Discover, which was born out of a BBSRC project. So we were able to cover some scholarships and travel to attend 4 courses for 25 people in Python coding, data handling, machine learning, and AI. Again, with the idea to get these skills into the bioscience community. We're hoping to be able to do something similar to this again before the end of the project. Again, best way of staying in touch is to sign up for that newsletter if you want to hear about more opportunities like that. I mentioned collaborations. Again, if anyone is thinking about putting on an event in the imaging space, AI imaging, for example, in BBSRC remit, talk to us. We might be able to co-host it in some way. We've worked with, I need to update the slide actually, because this is last year's, but loads of different organizations running loads of different kinds of events. Everything from us co-funding events through to maybe just helping to advertise it or turning up and telling everyone about AIBIO. So there's the kind of complete range of things that we can cover. If you are running an event, probably the easiest way to get some money towards it is via our Flexi Fund. So this is a very light touch application for funding up to about 3K that you can use to help put on an event. So for things like paying for travel scholarships for ECRs or helping get room hire in a venue that you were struggling with. We all know that money's tight at the moment for running things like events, getting to events. So this is a way where it's a relatively easy way where as long as the event is in the AI bioscience space and we're adding some value, so bringing ECRs or holding it somewhere where you wouldn't be able to hold it otherwise, put in the application, we regularly review it. And as long as it's within remit at the moment, we normally fund it, or we'll talk to you about how you can reduce the scope or something like that. So for most events, that's probably the best way to do it. If you're thinking about a research project, that's not suitable for the Flexi Fund, but as I mentioned, the pilot funding is coming up. We do occasionally run, if you like, fully fledged joint events as well. So jointly running a conference or a workshop or something like that. If it's really in the crossover space and there's something that we can add, then we're very happy to have that discussion. But best thing to do is drop us an email on the website if that's something that you're thinking about. Lastly, I'd just like to invite you all to think about attending our third annual conference now. So this will be in Aberdeen, beginning of June. And we're inviting poster submissions. We've got some keynote speakers. We have some workshops from MATLAB, so MATLAB workshop and another data analysis workshop. It's, really it's about what AIBIO does best, which is bringing people together. So it's really a kind of networking type meeting, but also a chance to talk about your research and hopefully get some people interested in it and maybe building up some collaborations. So if you're interested, have a look at the website and sign up. And we do have some a limited number of scholarships that you can apply for as well for that. And there's more details if you follow the application process. So that's it. I'll stop there. Thank you very much for your time. I realise I've gone on a bit, but happy to answer any questions that have come through about computer vision work or AIBIO.
Okay, thanks. That was great. That's very very interesting, and I think some of it was definitely relevant to our directly relevant to our community. So we have one question in the Q&A. I think last time we didn't have the power for that person to speak, so I'll read out the question. It's from Sony, who you know.
Yeah. Hi, Sony.
So, what do different levels of fluorescence imply? And I think this is going back to the
so going back to the
lab
images. I may have already answered that question in the talk, but basically nothing. It's an artifact of the imaging process. So it's either that particular part of the plant architecture is not autofluorescing as well. So that could be the structure of the cell wall, the moisture, or some other artifact of the kind of material it is or where it's located in the structure. Could be that, or it could be literally an artifact of the imaging process. So depending where the laser is when the image is taken, it may be fluorescing more or less strongly. So the answer is biologically nothing that we can infer. It just becomes a bit of a nuisance for the image analysis. And that's why we do that two-step process. The first step really throwing away the different levels of fluorescence in order to just get a structural image out.
So perhaps I can ask a question on the LAT as well.
Sure.
I mean, you focused on the segmentation once you have a 3D stack, but presumably there's also a step of aligning the individual 2D images first, which has to take into account distortions and
Correct.
errors and noise. Is that, and because that is quite similar to what we might do in like FibSem or something like that.
Absolutely. Yeah. So you're right. So again, what you're doing is you're firing a laser at the end of the plant, and it's gradually going away like this, and so you're getting physical effects on the stem as it's burning away. So you're getting some distortion because of the physical process that's happening, and they should be fairly well aligned because you're going to get some movement maybe, but the stage and the camera are quite carefully controlled. But yeah, however, there will be an alignment process, and I'm trying to remember. Yeah, I realised as I was talking through these slides, I didn't have a nice 3D fly through of the final kind of reconstruction. But that's definitely done. And there are 3D segmentations of the cells. And I feel like there's kind of a non-linear shear transformation that tries to match up the images between the slices, which is part of the pre-processing, but yeah, I can't tell you the exact details.
Yeah, I would imagine that you would need some kind of shear transformation to cope with
Yeah.
distortions. I would guess that. Yeah. Um, Again, I mean, maybe ask a second question, which may more technical, but maybe closer to the hearts of people watching. How, from representing the AI bio community for BBSRC, how do you feel about the investments into HPC platforms? These new platforms in Bristol and Cambridge, which are dedicated for AI applications. Is that something that you had input into? Is it something that you think is useful for the community, or?
Yeah. So it's good question. So it's not something that I had input into directly, though we made the community aware of various surveys and things that were happening about it. I must admit, in Nottingham, we tend to do all, because of the kind of AI that we're developing, we tend to do it in-house on our GPU servers. That said, I believe the facility, the Isambard facility at Bristol, is very well suited to sort of modern AI approaches, and that's, I guess, part of the point of it, isn't it? So a lot of
Yeah,
GPU type compute, as I understand it, which is very different to a lot of the traditional CPU type supercomputer access. Um, there's much more of a demand for parallel processing on GPUs rather than just number of cores of CPUs. So yeah, not much I can say really. I don't have a lot of experience of it directly, and I guess especially, you know, being quite new, we'll see how they get used and the best way of using them. Um, yeah, I don't know whether you have any
yeah.
comments, Martin.
Um, no, I mean, it's not something I have direct experience of either. I've just been watching. I mean, there is an issue of convenience, that it can be is a lot more convenient to use a local
Mm.
um,
Well, it is and it
workstation.
isn't. So I think, to be fair, there's a large overhead in keeping everything running,
Yeah,
and you don't have that with anything remote. But then on the flip side, certainly for us, I think data transfer is always can be problematic, and I imagine that's true in your world as well. We often work with data sets that, where each image may be tens of gigabytes potentially, if we're talking about micro CT or something like that, or the LAT even for a full stack. Um, And so shuffling that data around, especially doing what we do, which is developing AI. I think if you're running an AI model and you want to run it on 10,000 images that you've captured, it's more of a fixed pipeline process. But when you're developing AI, you've got that iterative, oh, I've got to get the code working and tweak it and get it back and change things and change how I pre-process the data. There's definitely an advantage to local compute there, I would say. But if you've just got a massive amount of data to process, then remote compute probably works out cheaper and more convenient because you don't have to support it. But yeah, we're on the development side rather than kind of the rolling out the model and just analyzing a load of images side. It'll be
yeah,
interesting to see what
no,
happens.
yeah. But I mean, I agree. I mean, they actually, I mean, for us, it varies a lot depending on the technique. But at least for some, where we're going for electron tomography, then yes, the data sets can be quite large, and
Mm.
there is an issue of whether you spend more time trying to get the data sets there than you actually do processing
Yeah,
them.
it's always an issue, I think, is transferring data or whatever you're doing, versus the costs of just hosting it and backing it up locally, which can also be problematic and potentially quite high cost. So yeah,
Data's a problem.
data's a problem in conclusion.
Um, right. I don't see any other questions, although people are still listening in.
That's
Um,
fine. you know, I appreciate it's not your core area, so maybe people need to either I've been completely clear, or more likely it's just been too confusing.
No, I think it's completely. I mean, I would say, as I said before people joined, you know, this, well, where structural biology is moving into in situ studies, then these issues of image stitching or stacking and segmentation, I think, are becoming more relevant.
Mm-hmm.
There are also other kind of edge cases where people, you know, in crystallography, people try to image the crystal itself to find out where it is, and that also leads to imaging problems. So there are kind of technical.
Yeah. Sorry to interrupt. I was going to say, perhaps I'd leave you by saying that, you know, both the Computer Vision Lab and AIBIO, if it wasn't obvious, we're really open to collaboration. So if you've got a computer vision problem, then reach out, and you never know whether it's going to lead to a PhD studentship or something like that. I mean, the 3D micro CT synthetic data work was with the Franklin, with Mark Basham, and you know, there are various opportunities to build computer vision into different kinds of projects that you wouldn't automatically assume there was kind of a straightforward fit. So we're very, very happy to have a quick chat and have a look at some images if you think you've got an interesting problem.
Okay, that's good. Yes, I mean, I know Mark. It's a nice link. But yes, I think that was the call to everybody listening to make contact.
I'm not promising I can solve your problems, but I'm happy to talk them through.
And Andrew will solve any problem you have.
For a fee. Okay.
Okay. Thank you. So, and Bindu, do you have an advert to give, or are we not ready yet?
Yeah, I don't have the title, but I know the speaker and the date. So our next speaker for DRIIMB webinar series is Alexander Bonvin from Utrecht University. So his webinar will be on 29th of April. So there is a lot of time. So I'll announce it towards the end of this month. Yeah, I hope we will see you there.
Good. Okay, I guess we can wrap up then. So yeah, thanks very much again for your talk, and good to see you.
Thanks for joining. Thanks for the invite.
Yeah.
Thank you, Andrew, and thank you, everyone.
Yeah, thanks everyone for joining.
Yeah.
Okay, bye.
Bye.